So in Chapter 7, we are introduced to the idea of the pain matrix. So the pain matrix is basically brain structures that process and regulate pain information. And the interesting thing is that the pain matrix structures are capable of creating pain perception in the absence of nociceptive input. So sometimes we can have a very simplistic idea of like, oh, you stimulate a nerve in the periphery and it causes pain in the brain. And that is absolutely not what usually happens. Nociceptive input is part of it, but the pain matrix in the brain is capable of creating pain even in the absence of nociceptive input. So the pain matrix includes parts of the brainstem, the amygdala, which functions in emotion, the hypothalamus, autonomic function, the thalamus, and areas of the cerebral cortex. So that whole pain matrix affects the perception of pain. The experience of pain is strongly linked to emotional, behavioral, and cognitive phenomenon. So what I was saying about the therapeutic neuroscience education, where you tell people how pain works, and that actually allows them to control their pain better. In reaction to nociceptive signals, the pain matrix generates a top-down response that regulates ascending pain signals, depending on psychological, physiological, social, and genetic factors. The pain matrix can amplify or suppress nociceptive signals. So it can say, no, we're not going to perceive that as pain. We're going to ignore that. Or, well, we're going to make that a lot worse. We're going to perceive it as a lot of pain. So the pain matrix determines whether ascending nociceptive processing will be normal, suppressed, sensitized, or reorganized. So two terms that we're going to talk about are AntiNociception, which is the top-down inhibition of pain signals, and pronociception, which is the biological amplification of pain signals. So AntiNociception makes pain better, pronociception makes pain worse. Makes sense, right? So in Adrian Lowe's educational materials, the therapeutic neuroscience education, he talks about how when functional MRI studies are done, and we have some pictures from the book, certain areas of the brain light up. Certain areas of the brain are involved in a pain response. So those areas in the brainstem, amygdala, hypothalamus, thalamus, areas of the cerebral cortex, including the prefrontal cortex, which is our decision-making, areas having to do with arousal and concentration. Lots of areas of the brain are involved in pain. So when you're experiencing pain, whatever the cause, whether it's top-down or bottom-up, those areas of the brain that are involved are not able to pay attention to other things. So it's going to affect your concentration, it's going to affect your mood, it's going to affect your immune system. So there are lots of different effects from pain. So we need to talk about antinociceptive systems and how pain is controlled. So we talked a little bit about Gait Theory in modalities class. So the pain matrix, it's those brain structures that process and regulate pain information and are capable of creating pain perception in the absence of nociceptive input. So we don't have any A deltas or C fibers telling us anything. The pain matrix is just telling us there's pain. So there are certain chronic pain syndromes, which we will talk about a little bit more, such as fibromyalgia, that create pain in the absence of nociceptive input, which is kind of not fair. So here's our little pain matrix chart, and it uses the arrows. The descending arrows represent top-down control of nociceptive signals by the pain matrix. The black arrows are anti-nociception, and the green arrows are pro-nociception. So you're getting, the red arrows are bottom-up signals. So you're getting, the red arrows are nociceptive input, the green and black arrows are pain matrix input. So I don't expect you to memorize this chart, but obviously there's a lot of input. And so you can have nociceptor input that causes pain. You can have nociceptor input without pain. You can have pain without nociceptive input. There's lots of different combinations, and it's controlled by the pain matrix in the brain. So, as I said before, the experience of pain is strongly linked to emotional, behavioral, cognitive, and genetic phenomenon. There's an actual difference. There's a difference in functional MRI studies of how men and women perceive pain. There are 9 areas generally that are lit up in a functional MRI when someone's experiencing pain, and they're the same in men versus women, but in women, some of the areas, the stimulation persists longer. They don't have the same recovery from pain. And there's some differences in children even between girls and boys. So, and interestingly enough, in younger boys, there tends to be more pain activation and more reports of headaches and that type of thing. Once they go through puberty, that diminishes. In girls, it's just the opposite. In younger girls, there's not as much report of headache and pain, and then once they go through puberty, there are more reports of widespread pain and headaches in girls versus boys. So really interesting gender differences, and so obviously there is something else going on besides just nociceptive input. So the pain matrix, understanding the pain matrix requires the consideration of discriminative pain sensations, motivational and affective pain sensations, and cognitive and evaluative components of pain. So sometimes I'll be working with someone in the chronic pain education program, and people tell you stuff in therapy that they probably wouldn't tell anybody. But you spend a lot of time with people, and they'll tell you some pretty private things. One time I was working with a lady in the chronic pain program, and she was telling me all the stuff that was going on in her life. And holy cow, there was a lot of stuff going on in her life. And I said to myself, I said, boy, if I had all that stuff going on in my life, I think I'd be in pain too. Work stress, emotional stress, family stress, they can contribute to pain, lots of different things. So the discriminative aspect of the pain matrix refers to the ability to locate the site, timing, and intensity of tissue damage or potential tissue damage. So the other things, though, don't have anything to do with tissue damage. Another thing that can affect pain that's sort of on the motivational, affective, and cognitive evaluative side of it is what we call catastrophization, which is where people say, like, the doctor tells them, oh, you have degenerative disc disease, and they've never heard that before. I mean, in PT, we hear that every day. It's no big deal. We don't get excited about it. Everybody's got degenerative disc disease at some point in their lives. But people go, oh my gosh, degenerative disc disease, this is horrible. I'm never going to be able to work again. I probably won't even be able to move without pain. That's what I refer to as catastrophization, and that can drastically increase somebody's pain. Or like my patient that I talked about earlier, who had some increased pain with a new exercise, and she thought, oh my gosh, there's something horribly wrong, and her pain went way, way up. Once we reassured her that there wasn't anything wrong and she was healing just fine, her pain went way, way, way down. So none of that had to do with nociceptive input. It all had to do with her motivational and affective and cognitive evaluative areas of her brain. Very interesting stuff. No tissue damage, but the pain was way up. So the motivational affective aspect refers to the effects of the pain experience on emotions and behavior, including increased arousal and avoidance behavior. Cognitive evaluative refers to the meaning that the person ascribes to pain. So my patient, the meaning that she ascribed to the pain is, my shoulder is dislocated. It wasn't, but that was the meaning that she ascribed to the pain, and caused her pain to increase. There can also be emotional rewards, basically, for staying in pain. It could be the person gets more attention because of their pain. It could be they hate their job and they don't want to return to work, and by still being in pain, that allows them not to return to work. So there might be some sort of secondary gain involved. People don't do this stuff on purpose. This is very much on the unconscious level, but what comes to the conscious level is pain, and that's what the patient feels and understands. And pain is real. People's pain is real, whether there's nociceptive input or tissue damage or not. We have to validate that to patients, that their pain is real, and we respect that their pain is real. That doesn't mean that there's a physical basis for it, but it does mean that we can help them. So just acknowledging to the patient that you understand that their pain is real, that can be very reassuring to them, and that can help them reduce their pain. It's a huge, big deal. So this is another graphic from the book, and it just talks about the contributions to the experience of pain from brain regions that respond to pain signals. So just suffice it to say that there are lots of different, and this separates sensory, emotional, motivational, and cognitive aspects. There are lots of things that can contribute to the experience of pain from different inputs. So we talked about gait theory last quarter. So the typical response to, say, hitting your thumb, you withdraw the thumb, you yell, you apply pressure. So the Melzack and Wall Gait Theory of Pain in 1965 kind of came up with the first scientific explanation of how pressure and other external stimuli inhibit pain transmission. So some of the details of the original gait theory are now thought to be incorrect, but the original theory is important because it inspired inquiry into the mechanics and control of pain, such as using TENS to help control pain. So sort of the modern version of gait theory is counterirritant theory, which incorporates finding from that original research and the research that was stimulated by the gait theory research. So the counterirritant theory explains the inhibition of nociceptive signals by stimulation of non-nociceptive receptors occurring in the dorsal horn of the spinal cord. So that's our A beta fibers are the non-nociceptive receptors, and they're inhibiting the C fibers and A deltas, the nociceptive inhibitors, and it's happening in the dorsal horn of the spinal cord. So the processing of somatosensory information in the dorsal horn can be altered by abnormal neural activity or by tissue injury. So I talked about this a little bit earlier. The 4 states of dorsal horn processing of nociceptive information are normal, suppressed, sensitized, or reorganized. Okay, and we'll talk about them. So AntiNociception is a suppression of pain in response to stimulation that would normally be painful. Endorphins are endogenous substances that activate antinociceptive mechanisms. Opiate receptors are receptor sites that bind with both endorphins and opiates. So I think it's amazing that we have these receptors in our bodies that are really meant to bind with natural endogenous substances, endorphins and enkephalins and that sort of things, to activate those pain control, those antinociceptive mechanisms. But the thing that I think is amazing is that there's a plant out there in nature that produces substances that also bind to those receptors. So, wow, that's I just think it's amazing. I don't have anything more to say about that, but we're going to talk about levels of antinociception, and those endorphins and endogenous opiates are one of the top-down antinociceptive systems. So these are way too small to see right in here. And we're gonna talk about the levels that biological amplification of nociception and increased nociception. So we're going to talk about that in the next section.